Welcome to the Hitchhiker's Guide to Calculus. My name's Kevin, and I'll be your guide to Chapter 2.2, the definition of the derivative function. If you watched our last video, you'll recognize this graph, albeit with a couple changes. On the x-axis, we're going to distinguish between 2 points, x and x plus h, and their respective y values. So this first point on the left would be x f of x, and the point on the right would be x plus h, f of x plus h. Our task will be to compute the slope. And we know slope is y2 minus y1 over x2 minus x1, but utilizing the points here at our disposal, we've got f of x plus h minus f of x all over x plus h minus x. We see the x's here in the denominator will cancel out, so we can clean this up into a slope formula of f of x plus h minus f of x all over h. Now this computation would calculate what we would call the slope of the secant line, which is just a line that connects 2 points on a graph. I've drawn it here. So we're computing the slope of this line. But for the derivative, we don't want the slope between 2 points. So I'm going to erase that, and I'm just going to draw an arbitrary function, continuous one, that connects these 2 points. And the slope that we've computed so far, you could call the average slope of this function between the beginning point and the ending point. We want to find the instantaneous slope at x. So what we're going to do is move that ending point closer and closer to our starting point, x, f of x. And as we move the x-coordinate, x plus h, closer and closer to x, we're making h smaller. And if I put a point closer to x and I draw another secant line, we can see that the slope slightly changes. We move our point a little bit closer, draw another point on our function, connect it again, we see another secant line and another slope. We progress just like this, moving our point closer and closer to x, essentially making h closer and closer to 0. And we take that idea and put it into a limit, giving us the limit as h approaches 0 of f of x plus h minus f of x all over h. Now again, all this is the slope formula, but it's the slope when I move one point closer and closer to another point, essentially merging them into 1 point. And we call this the derivative as a function of x. We would write it as f prime of x. Now I want to emphasize before we move on that all we're finding when we find f prime of x is the slope of the tangent line to f of x at any value x that we want. Now let's apply this to an example. Let's find f prime of x for the following function, and then find f prime of negative 1. The function in question will be x squared minus 1, and in order to find f prime, we just learned that f prime of x is defined to be the limit as h approaches 0 of f of x plus h minus f of x all over h. Now to compute this, we're going to have to take a few steps. First and foremost, we need to figure out what f of x plus h is. To do this, we'll simply substitute in x plus h every time we see an x, so that'd be x plus h squared minus 1. If we multiply out that x plus h squared, we should get x squared plus 2xh plus h squared minus 1. You can verify that. And that's the expression that we're going to need to substitute into our limit. So step 2 is substitute our expressions into our limit. This would get us the limit as h approaches 0 of f of x plus h, well that's x squared plus 2xh plus h squared minus 1, minus our original function x squared minus 1. I want to put these in parentheses to indicate that I am subtracting both functions. And now we just want to simplify and clean things up. We can see in the expression right now, we've got an x squared here, minus an x squared over here, those will cancel, and a minus 1, minus negative 1, also canceling. If we throw those out and start to simplify this, we'll see that we have the limit as h approaches 0 of just 2xh plus h squared over h. Both these terms in the numerator have an h in them, so we can factor that h out, leaving us with h times 2x plus h over h. Now we see the h's can cancel out, leaving us with the limit as h approaches 0 of 2x plus h. Finally, we plug in 0 for h, and we get 2x. So that means that our derivative, f prime of x, is equal to 2x. We'll finish this problem on the next slide. Here we'll just continue our process from before. We have the function x squared minus 1. We just learned through our process that f prime of x is equal to 2x. And we still had that final question to fill out was, what is f prime of negative 1? Now, this should be the easy part. We already have the derivative function, which tells us the slope at any value of x we want. So we can just plug in negative 1 and find that f prime of negative 1 is equal to negative 2. That's simple enough, but let's investigate and really hammer home what this means. This tells us the slope of the tangent line to f of x equals x squared minus 1 at x equals negative 1 is negative 2. Now we put this on a graph. I think it's going to cement this thought for all of us. Now we know what our original function x squared minus 1 looks like. That's a parabola shifted down 1 unit. So I'm just going to draw it in here and label it appropriately. If we take a look at the point on our function at x equals negative 1, that's right over here on the left side, and we were to imagine a tangent line to that function, at that particular point, we can see that it has a slope of negative 2. And I did a pretty good job drawing it in here, freehand. If you calculate that slope, rise over run, it looks like it's going down 2 and to the right 1. So it does have a slope of negative 2 at that very specific instant in time when x equals negative 1. And that's it. That's exactly what a derivative function tells us and how to use it. Be sure to check out our next video to learn some shortcuts to finding this derivative function. Don't forget to hit subscribe and like the page to get alerts about all the content we release each week.